All right, so we're going to go ahead and continue talking about a different type of energy called gravitational potential energy. Okay, so the idea is that we're looking at the work that's being done in order to lift an object straight up, okay, at some constant speed. So the equation here is the mass times the acceleration due to gravity times the height. So here we have somebody holding a ball, and she's holding it at some height. Okay, let's call it h. Now, if she drops the ball, now it's at some different height. We'll call it h prime. Okay, so using or looking at this potential energy equation, which one would have the higher potential if this one is larger than this one, the heights? The height is larger than this height. This potential energy would be higher, right? So this potential energy, I'm going to call it 1, would be higher than the second potential energy, if this is 1 and this is 2. Okay. One thing to note, during the ball falling, okay, the potential energy is transferring into kinetic energy, okay? So remember how before I say that one energy can turn into another energy back and forth? This is exactly what is going on here. As the ball is dropping, my kinetic energy increases, okay, until just an instant before it hits the ground, or at the instant that it does hit the ground, my kinetic energy will be at its peak, okay? But my potential energy will be at its lowest. Okay, so at this point, my potential energy is at maximum, okay? And since the ball is not moving, we don't have any kinetic energy. Our kinetic energy is 0, okay? And that, again, comes back, or that comes from the equation of kinetic energy being related to velocity. Okay, so if my ball is not moving, then it is going to have a kinetic energy of 0. Okay, and again over here, my kinetic energy, or my potential energy of the ball transfers to kinetic energy. Okay, so I will go ahead and show another example where there's an energy in, or the guy is pedaling, okay, up this hill, and we have kinetic energy, we have some kind of motion. At that peak, we have the potential energy is going to be at its maximum, and then we have energy out, and again, that turns into kinetic energy. Okay, now let me go ahead and talk about potential energy in general. Okay, and that is the potential energy is just the energy of a system that is due to its configuration, its shape, its position. So it's basically stored energy. Okay, so potential energy is the stored energy. Okay, so like this one, in this example, there is an energy that's being stored because she has pulled back that arrow. Okay, so there's some potential energy here. Okay, as she releases it, it turns into purely kinetic energy. It is now moving. Okay, so we have some kind of kinetic energy here. I also wanted to mention conservative forces, which is going to be any type of work that's done, and that work does not depend on the path that is taken. Okay, and I'll talk about that in a minute here. So I looked at just one type of potential energy, back here, okay, gravitational potential energy, but we also have spring potential energy, okay, or the potential energy of a spring. So the first thing we would need to know is how to calculate, how to calculate the force of a spring. Okay, so that is going to be equal to negative k times x. Okay, hold on. Now what is k? K is a spring constant. So spring constant. Okay. So it's just a value to measure, I guess, it's type of force constant. So think about it this way. If you're feeling a spring and it's kind of hard to press or extend or compress, it'll have some different spring constant than one that is very easily to move back and forth. Okay, so that's how it's described. So now we know X, again, is just our displacement. Okay, so this time it'll be a displacement of a spring. Okay. We also have potentially a string. It has the same idea. Okay. So we have the potential energy is going to be equal to 1/2 times my spring constant times the displacement squared. Okay. Now this displacement is from its equilibrium point. Okay, so if this A is equilibrium, is at its equilibrium point, and we extend the spring to some X value, okay, so our displacement is X. Okay, so our displacement, again, is going to be from its equilibrium point. Okay, so hopefully that makes sense. Basically, it's something like if this body was at rest, okay, that's where it would be at equilibrium. Okay. All right. So looking at conservation of mechanical energy, excuse me, we are first assuming that we only have conservative forces. Okay, and I'll talk about the difference between conservative and non-conservative in a minute here. But we come up with these equations here. Okay, so first of all, I'd like to point out that the mechanical energy is defined as our total kinetic energy. So our total kinetic energy plus our potential energy of a system. Okay, so that's going to be our mechanical energy. That's what that is defined as. Okay, and if we're looking at conservative forces, we can state that our change in kinetic energy, which is really just kinetic energy final minus kinetic energy initial, okay, plus our potential energy change, or change in potential energy, is equal to 0. Okay, so this is the idea of conservation of mechanical energy. Okay. Now we can rearrange that to get into this form. Okay, so move a couple of things over and then we'll get into this form. The initial of the kinetic plus the initial of the potential equals the final of each, added together. Okay, so now we are going to use this idea, okay, to solve another example. Okay. Okay, so we're going to be looking at example 7.8 here. And we have this situation where we have a toy car with this mass of 0.1 kilograms, and it is propelled by a spring, okay? The car follows a track, as you can see here in this illustration, that rises 0.18 meters above the starting point, or 18 centimeters, okay? The spring gets compressed 4 centimeters, okay, and has a constant, or has a force that's constant, has a sorry. Oh, a force constant, sorry, like a spring constant. That threw me off. Okay, so spring constant, there we go, of 250 newtons per meter, okay? And we are assuming work done by friction is negligible, so we're not gonna worry about that. And so we need to find the following. The first part states that we wanna know how fast the car is going before it starts up the slope here, okay? So I'm gonna go ahead and draw on this. I'm gonna say that's the point where we wanna know how fast the car is going, okay? So I'm gonna go ahead and use this space over here to write what we know. We know the mass of the car. We also know some height that it rises. We don't need to use this right now since we're only looking at it from when the spring hits the car, basically, or the car loads back on the spring and then is let go to this point right before it starts going up this little slope here. So we don't need to worry about this yet, but we'll go ahead and write that down for a minute. Now, the spring is compressed, okay, and I'm gonna call that X, and it's compressed by 4 centimeters or 0.4 meters, okay? And has a force constant or a spring constant K of 250 newtons per meter. Okay, so this is all the things that we know. Okay. Now we are wanting to know the speed right before it starts up the slope. Okay, so we are looking at for some speed here. Okay, so let me go ahead and scroll a little bit. So I'm gonna say we wanna know some final speed. Okay, and what we can do is like we had in this equation here, my kinetic energy and potential energy, I'm gonna go ahead and use that formula, okay? So I'm just gonna write a K for kinetic energy and a P for potential energy. Hopefully that's okay with you guys. Okay. Equals to final kinetic and final potential. Okay. Now we can write out this with all of the equations. So, oops. We have 1/2 mv naught squared, okay? That's our kinetic energy, plus our potential energy, which is going to be, let's see, mgh. I'm gonna put h naught, okay, for our initial. Okay, plus our our potential energy of the spring. So this is our gravitational potential energy, and now we need our spring. So that's gonna be 1/2 kx naught squared, okay? So this is for our spring, equals 1/2 mv squared. I'm gonna go ahead and leave off the f, that way we don't get it too crowded, plus mgh plus 1/2 kx squared, okay? So let's note a few things. So if our starting position is here, then our final position that we're looking at is here, okay? Our initial velocity for this car is 0, right? So our initial velocity is 0. The car is not moving until it's pushed. Okay, so this term actually goes away. That first term. Okay, let's look at the next term here. Let's see, our mass is constant, our G is constant, our H naught, we can go ahead and label this as H equals 0 right here. So the height at that point is going to be 0. So our initial H naught, is 0 meters. Okay. Now we do have, so this term also cancels. We do have in this spring potential energy that our X, or our X naught, okay, this displacement of the spring is non-zero. Okay, so that is non-zero. I'm gonna go ahead and write non-zero. So we keep this part of our equation. So these two canceled since we had 0 values, but now we have this 1/2 kx squared, okay, equals. Now let's look at the other side. So this other side, our mass is constant, of course. Our velocity, that's actually what we're looking for, our final velocity here. So I'm gonna go ahead and keep that since we wanna know that velocity. And so let's go ahead and continue. So this is our, I'm gonna go ahead and write unknown. And give me 1 second. Okay, so again, we just placed in our second part of our equation. Now let's look at this part here. Our height, we're looking at it right before it starts up this slope here. So our height here is gonna be 0, okay? So that cancels this term as well. Now looking at this last one, we actually don't have a spring on this side, right, at the final here. So we don't have this potential energy, okay? So we are just left with this simplified equation, okay? So let's go ahead and solve for our velocity, okay? Our 1/2s cancel. I'm gonna go ahead and move my mass to the other side. So I get k times x squared over m, and this whole thing will be squared, or square rooted, I'm sorry. So we can plug in our values. Whoops. So our spring constant k is 250 Newton per meter times our x naught, or x, it's 0.04 meters. Okay, and that's going to be squared, divided by our mass, which is 0.1 kilograms. 0.1 kilograms. And this will be square rooted. Okay, so our velocity ends up being 2.0 meters per second. Okay, and again, you always want to make sure that you're checking your units. Okay, so we can double check them by saying we have a Newton over meter, and then a meters squared over kilograms. This whole thing is square rooted, so just looking at the units again. Okay, that is going to be kilograms meters per second squared. Okay, and then meters squared over meters kilograms, again all in the square root. So let's see, one of these cancels with one of those. Okay, my kilograms cancel, so I end up with meters squared over second squared in the square root. So that gives me meters per second. Good. All right, just checking to make sure that we're getting our right units, because remember, units are very important in physics and in life in general, okay? So we found how fast the car was going right before it starts up that slope. So that is at this point here. We found that. Now, for part B, we want to know how fast it's going at the top of the slope. Okay, so that's going to be at this point here. Okay, so we're going to use the same procedure, okay, but now we may not cancel the same things out. Okay, so let me go ahead and zoom out a little bit and scroll down. Okay, so for part B, we are looking at, oops. We can look at this equation again because we're going to be doing the same thing. So let's see. Our initial velocity again is going to be 0, so that's going to be canceled out again. Our initial height is again going to be 0, so that one's going to be canceled out again. Now our spring displacement here is non-zero, so we're going to have this term again. So let me go ahead and scroll down and say that we will have our 1/2 kx squared. Okay, so that's what our left side is going to look like. Let's look at our right side. We're looking for our velocity, our final velocity. So again, we're going to have this part. This next one, we will have some kind of height here, since now we have moved up that slope 18 centimeters. Okay, and then again, no spring, so we're not going to have that term. So we're going to have these two terms though for this one. So we're going to have 1/2 mv squared plus mgh. Okay. So let me go ahead and define a couple of these. So my x is above, my v is unknown, but my h is going to be that 18 centimeters. Okay. I'm going to go ahead and write down my x. That was 0.04 meters, and my k, 250. It's always good to keep track of all of these numbers. I'm getting tired of scrolling up and down, but writing them out a couple of times doesn't hurt. Okay, so again, we're looking for our velocity. So we can rearrange this equation to this here. We're going to have 1/2 kx squared minus mgh. Okay, we're going to solve for v squared. So we're going to have 2 divided by m times that 1/2 kx naught squared minus mgh. Now we can pull in that 2 or leave it out. It's up to you. Might make it a little easier, and the m. So I'm going to go ahead and do that. I'm going to get k over m x naught squared minus 2gh. Okay. But again, you could leave it in that other form. Doesn't really matter. As long as you plug it into the calculator correctly, it's fine. Okay, so now we want to square root. So we can plug in our values. We have k, which is 250 Newton meters, divided by my mass, which is 0.1 kilograms. Okay, and then that's multiplied by our displacement of the spring, minus 2 times 9.8 meters per second squared, times our height, which is 0.180 meters. Oops. Okay. Now all of that is going to be under a big square root. Okay. And so our velocity turns out to be 687 meters per second. Okay. So that is going to be our velocity at our height, h. Okay. So if you think about this just for a second, and don't worry about all of the calculating that we just did, okay? If we're looking at a toy car and we push it back on a spring and let it go, okay, our velocity when it hits right before the slope is gonna be faster than as it travels up the slope and gets to that peak, right? Because it's losing energy as it goes up, okay? It's losing kinetic energy. So it's slowing down as it goes up there, okay? So sometimes when we're looking at physics problems, we kind of get caught in all of the numbers and all of the details of the math that we kind of get lost at what it really means, okay? So again, logically, this makes sense for the car to be losing energy and velocity as it travels up that slope, okay? All right, so I'm gonna go ahead and stop this video and then we'll continue with our next video.